Today, we're diving into the fascinating world of temperature inversions, a phenomenon that plays a crucial role in our weather and climate. You know how the air gets cooler the higher you climb a mountain? That's normal. It's a pattern we see every day. Usually temperatures decrease as we go up in the atmosphere. This is a fundamental aspect of how our environment works. It's like climbing a giant staircase, and each step takes you to a slightly colder level. Imagine each step as a layer of the atmosphere. This natural temperature gradient is important for our weather patterns. It influences everything from wind to precipitation. Think of a hot air balloon. The way it rises is a perfect example of how temperature affects air movement. The hot air inside is lighter than the cooler air outside, so it rises. This is due to the difference in density. The same principle applies to our atmosphere. Warm air rises and cool air sinks, creating a dynamic system. Warm air near the ground, heated by the sun, tends to rise. This process is essential for distributing heat across the planet. This rising warm air carries away pollutants and mixes with the cooler air above, keeping our air fresh and clean. It's nature's way of maintaining balance. But sometimes, something interesting happens, a temperature inversion. This is when the usual temperature flow is flipped, trapping cooler air near the ground. Imagine a layer cake, but instead of frosting and sponge, we have layers of air. Each layer has its own unique characteristics, just like the different flavors and textures in a cake. A temperature inversion is like flipping the cake upside down. It's a fascinating phenomenon where the usual order of things gets reversed. In a temperature inversion, a layer of warm air sits on top of a layer of cold air near the ground. This is contrary to the usual situation where warm air rises and cold air sinks. This warm air acts like a lid, preventing the cooler air below from rising and mixing. It creates a sort of atmospheric cap that traps everything underneath. How does this happen? One way is through something called radiational cooling. This process is crucial in setting the stage for a temperature inversion. At night, the Earth's surface cools down, chilling the air just above it. This cooling effect is more pronounced on clear nights when there are no clouds to trap the heat. If the air above that is still warm, voila, you have an inversion. This warm layer acts as a barrier, preventing the cooler air from rising. These inversions can happen anywhere, from valleys to cities. They are more common in areas with specific geographical features that trap air, and they can last for hours or even days. During this time, pollutants can accumulate, leading to poor air quality and health issues. Remember how warm air usually carries away pollution? Well, during an inversion, that pollution is trapped under the warm air lid. Car exhaust, factory emissions, smoke, they all get stuck near the ground where we live and breathe. This trapped pollution can lead to a dangerous buildup of smog, especially in cities surrounded by mountains or hills. Smog is a mixture of smoke and fog, and it's harmful to our health. When we breathe in smog, it's like breathing in a cocktail of nasty chemicals. This can cause respiratory problems, irritate our eyes, and even worsen existing heart and lung conditions. One of the most devastating examples of the dangers of temperature inversions is the Great Smog of London in 1952. This catastrophic event is etched in history as a grim reminder of how human activities and natural phenomena can combine to create deadly conditions. A combination of cold weather, an anticyclone, which creates stable air, and the widespread use of coal for heating created a perfect storm for a deadly smog. During this period, Londoners heavily relied on coal to heat their homes. Unaware of the impending disaster, the inversion layer trapped the smoke and pollutants over London for days. This thick blanket of smog enveloped the city, making it difficult for residents to breathe and see. Visibility was so poor that people couldn't see their own feet. The dense fog reduced visibility to just a few meters, causing chaos on the streets and in homes. Thousands of people, especially the elderly and young children, died from respiratory illnesses caused or exacerbated by the smog. Hospitals were overwhelmed with patients suffering from severe breathing difficulties, and the death toll rose alarmingly. The Great Smog was a wake-up call about the serious health risks of air pollution and the role temperature inversions play in exacerbating them. It led to significant changes in environmental policies and raised awareness about the importance of clean air. This tragic event ultimately paved the way for modern air quality regulations and a better understanding of how to prevent such disasters in the future. Temperature inversions are fascinating meteorological phenomena that can have a significant impact on our environment and health. By understanding how they work and the problems they can cause, we can work towards cleaner air and healthier communities. Remember, science is everywhere, even in the air we breathe. Stay curious, my friends.